Sorry, IV characteristics. Oh my goodness. Yes. What's wrong? Hungry? I know, I'm so hungry as well. And I have a class at 1 o'clock. Do you?
No.
No, I do. Maths class. So when you're eating your lunch, think of me. Okay?
When is your break?
2 o'clock. I had class at 9 o'clock. Did you? Yeah. Okay.
We only start at 9 o'clock.
Every day?
Every day.
Sucks. Well, you finish at 5 o'clock every day?
No.
No. So that's interesting. That's better, actually. I think so.
Yeah.
Don't you? No.
Finish at 4.
Well, you go to bed too late. This is your problem, I think. Yeah. 3 a.m.?
Often, sometimes.
Yeah.
She doesn't have a sleep.
Yeah, last night I went to sleep at, I think it was 2 a.m., 3 a.m. as well, maybe.
What were you watching?
I just couldn't sleep. I was just sitting there. I don't know why. I think I had too much coffee. So I got large coffee. This, I think, was the problem. Oh well. Okay, let's have a look now. Right, so let's look at the very simple circuit here. It's a very, very simple one. Do you remember what this is?
Open circuit.
No, this part, I mean. You should have it.
The various.
Not various. Variable resistor, which means you change the resistance here. Okay. Let's see what happens when we change the resistance here. If we increase it from 0 to a higher value. So let me just draw it, and you should draw it too. What do we have first? We have an OR here. We have a V here. We have an A here. And we have a variable resistor here. And I'll call this, I don't know, I'll call it X or something. And I'll call the voltage here, I'll call it E. We're good? Yeah? Okay. So, we don't have a voltmeter, but let's imagine we had one here. If I use my VI/OR triangle, the V here would equal I multiply OR, which is X. So, if I have the X at 0, what would this equal?
0.
It would be 0 volts, right? So if this is at 0, then the voltage here will be 0. Now remember that this voltage, let me just call it Vx actually, Vx. That voltage plus this voltage should equal total, which in this case is E. So if I make the X bigger, what happens to the Vx? It gets bigger.
Yeah.
So then what happens to the B?
Smaller.
Yeah, so this one will get smaller. Now let's see what happens to the A, okay? What is the current here? If you remember, the current will be V over R. And let's just look at the total, okay? The total current, which is this one here. The total current will be the total voltage, which is what? E, divided by the total resistance, which is R plus X. So if I make the X bigger, what happens to the I?
Smaller.
Yeah, it gets smaller as well. So this also gets smaller. So in other words, if I change this, if I make this bigger, then both of these will get smaller. Or the opposite. If I make this smaller, then both of these will get bigger. So my point is, as I change the resistance, the V's and I's will get bigger together as they get smaller together. So they move together. So if you were to make a graph, as the V gets bigger, the I gets bigger. Or as the I gets bigger, the V gets bigger. They both get bigger together, or they both get smaller together. And this is an important graph for the resistor. Let's have a look. So what we'll have here is that when the voltage is big, for example, the current is big because they move together. And when the voltage is small, the current will be small. And often we really want to know what graph this will make. So let's plot this data. Okay, let me just wait. I just want to check something here. Do I have any graphs? Come on. Oh man, I don't have any graphs. Alright, anyways, it doesn't matter. Let's go back to the data. So can you write this down as some example data from this experiment? Just make note of these. And then in a moment, I'll make a graph. What's wrong, Fuang? Graphs are great. What are you talking about? B I.
You should make this graph.
I'll make the graph. I just want you to write the data down.
Would there be any graph questions in the exam?
Oh yes. In fact, making this graph could be in the exam. I'll show you how to make it.
Have to do it manually though, by hand.
But you'll have graph paper. So it's okay.
Graph paper.
Oh, you know graph paper. Special graph paper.
The one like this.
Yeah, with the boxes.
Oh, yeah, okay.
Okay. Right, do you have this? Yeah, okay, so let's open up the spreadsheet. So the way we make these graphs for these experiments, we put the V here on the X and the I here. V and I. Sometimes people put I and V here, but I think really you're supposed to put V here and I here. So, V is in volts and I is in amps. What are the voltages? They start at 10, is it?
Yes.
And they go down to 1. Yeah, and then what does the current start at? And it goes down in 2s
Yes.
until... Okay. So, let's make the graph here. This is what you should have in your notebook. Let's have a look at it. Insert... insert chart. Scatter. I don't want this. Title is an IV graph. I for current, V for voltage. The x-axis is V in volts and y-axis I in amps. And let me just shrink this a little bit. Let me move you to here. And let me just close this one a little bit and this one a little bit. Okay. Right. So this is what the graph looks like. You have your triangle VIR. So if I was to work out OR in ohms, what's the formula for OR? V over I. So it's this one divided by this one here. And what you notice is that the OR for this graph is the same. So that might not surprise you, because you might think, oh yeah, of course the OR stays the same, you might think. So this is not a surprise. What is the OR on the graph though? If this is V and this is I, where's the OR here?
The line.
Well, what part of the graph? Well, let's have a look. Here. If I draw this graph here, this part here, delta X, that's the voltage, and this part here, delta Y, that's the current. So what is delta Y over delta X? That's current over voltage. So the slope is the current over voltage. But what's the formula for resistance? It's V over I. So actually, the slope represents 1 over the resistance. So in other words, when the slope is steep, the OR is small. And if the graph was like this, not so steep, then the OR is large then, yeah, big. So basically, this gives you the OR. Let's go back here. You can test it. For example, what's the height here? It's about 18 units. And here, what's that? About, well, I suppose it's about 20 and it's about 10. So 20 over 10 is 2. So then if I flip that, what do I get? 1 over 2, which is a half then, yeah? So these graphs, the x-axis is V, the y-axis is I, and the slope is 1 over the OR, which I think I maybe wrote on the next. Yeah, so this graph, wait guys, the name of this graph is called the IV characteristics, where you put the current against the voltage. And you change the voltage. Okay.
We should write it.
Yeah. So just if I go back to the picture here actually for a sec, just before you do. So what we really want to know is how does the I and V change for this resistor. So in the graph I drew, when the V gets bigger, the I gets bigger, and I think you can see in the graph how quickly the I gets big. Like here, oh where's my, yeah, so like here, for example, when the V goes from 2 to 4, you can see the I goes from here to here. You really want this graph, and I'll show you why in a minute, because this graph here, it tells you something about this resistor. How the I and the V change for this resistor, it tells you something about the resistor, and I'll show you what that is in a moment. Okay, so this graph is called the IV characteristics. Yeah, did you write this? Okay, you got that?
Yeah.
Yeah? Okay. Are we just waiting for you? I'll give you a few more seconds. Which part are you writing, Mahmood? Not that much time, come on. Right, great. Now, Ohm's law, don't write it just yet. Ohm's law says that for some materials at a low voltage and a low current and a constant temperature, the IV characteristic graph will be linear. So, it's not always true, but Ohm's law, he says that when the V is small and the I is small, that the graph will go through the origin and be a straight line. Now, the interesting thing is that it's not always a straight line. In the graph I did, it was a straight line. But in real life, it won't always be a straight line. It could be a curve. But Ohm said, if the I is small and the V is small, and the temperature is constant, then usually this will be a straight line. But not always, just usually. So, in my opinion, it's not even really a law, because it's not always true. So, the idea is just simple. Usually it's a straight line. Now, this is not always true. If it is true, then we say the resistor is ohmic. So, if the graph is a straight line, we say the resistor, where's it gone? We describe this as being ohmic if the graph is straight. And if it's not straight, then we say it's not ohmic. And we also looked at this already, that the slope represents the resistance, which I think you wrote this down earlier, but if you didn't, you can write it down. The slope is 1 over the resistance. So we're going to have a look at some more graphs. But have some people heard this before, Ohm's law? No? So basically, Ohm's law says that the graph is usually linear. If it is linear, we call it ohmic. And if it's not linear, not ohmic. Okay.
Do I have to write?
Yes.
Yeah.
Okay. What's wrong, Fuang? You have a question?
Why first love is 1 over R?
Yeah. Y 1 over R. So, here, this is V. Here, this is I. Yes? So the slope is I over V. But, if you look at the triangle, R is V over I. So this is not R, it's 1 over R. It's the wrong way. You don't look happy. In fact, you look shocked. What's wrong?
Why M equals in I and
Oh, if you have a line and you want the slope, the M, we say that it's, you got it? Oh, that's okay. That's okay. It's, for example, if this is 2 and this is 1, we say the slope is 2 over 1. That's what this means.
Delta y upon delta x.
Yeah. If the, for example, if the M is 3, we mean go out 1 and go up 3. That's what this means. It's the meaning of it. You did this in math class?
Yeah.
You did it like this, look.
Y2.
Y2 minus... Yeah.
I know that, but
Yeah, and that's the same thing. Delta y over delta x. Because if this is y2 and this is y1, then y2 minus y1 is this. Yeah? Okay, great. Alright. Yeah. Okay, we have this. Yep. Who's your maths teacher? Talk to him. Hey!
Don't mind me.
Are you just looking around, is it?
Yeah, right. Alright, nice.
Not in this room, I don't think. Okay, you have this? Yep. Alright, let's look at the next one. Right. So again, if you write the table down, I'll make the graph. Now wait, before you do, this resistor is a filament lamp. Wait! Who knows what this is? Filament lamp. No? Yeah. So what's a filament lamp?
The one attached.
No, I'll tell you which one. You all know. You know, on your study desk, you might have a lamp.
Yeah. The host.
Yeah, it has this shape to it. It has a circle base usually. Yeah, and then it has a square part here, and then a triangular part here. And it's usually very, very bright. And it's usually on your table. Do you know this?
Yeah.
Yeah, this is called a filament lamp. So this will be our resistor. Okay? So we change the voltage and we get different currents, and we want to look at the graph for a filament lamp. So if you can please just write this table down.
I want to be smart like you.
Me? Smart? No.
No,
This
you
is a
don't.
mistake.
No.
No, you shouldn't be thinking this now. It's all just a trick.
You can do everything.
I can do everything, not everything. Okay, you got this? Yes? Yes? Alright, so let's make the graph now. Is it still 10 to 1? Yeah. But the values are different here. The first one, 14. Next one,
13.5.
13.5.
13,
13,
12,
12,
11.
11, 10, 8,
6.2.
642, is it? Yeah, okay. So, let me see. The first part, part A, was to draw the circuit. So remember, you have a resistor, yes? Then you need to measure the current, and then you need to also measure the voltage. Oh, and actually, sorry, this resistor is now a light. So, like this. And then here, this lets us change the voltage, and then here is our power. So this is part A. So it's the same except it's a light here. Part B is draw the curve. Okay, so first I'll just actually draw this. Oh, by the way, there is a second way you can do this. Look. Or you can make the circuit like this. So far you're thinking, Stephen, this is the same, except this one here, this is plus, and this is minus, and this is a variable voltage. These are machines where you can change the voltage. Now you might say, oh, if you can change the voltage, why don't you use this instead of this? Well, there's a good reason for it. This is much cheaper than this. This is much, much, much cheaper. For example, this might only cost you €5, whereas this one be like €100. So it's much easier to change the resistance to make the change in the voltage than it is to change the voltage in the power supply. Yeah, so in the second picture here, what you're doing is you're changing the voltage here. This is more expensive than this way of doing it. If you change the resistance, you saw that these change as well. So this is the cheap way to change these, and this is the easier but more expensive way to change them. Guess which one you will use in the lab in semester 2? That's right, this one. Okay, but it's good to know for the exam that both of these are they do the same job. Yeah. Okay, B part. Use the data to make the curve. Well, there it is there. Now, is this a straight line?
No.
No, but is it a straight line at the start?
Yeah.
Yeah, and this is Ohm's law. So Ohm's law says if the voltage and the current are small, then it'll be a straight line. But for this material, it's a straight line, but then it curves. Is the ore big or small here?
Small.
No, big. Because remember, the slope is 1 over the ore.
Yeah.
So if the slope is small,
Oh, you mean the curve?
yeah, here.
Oh, okay.
If the slope is small, the ore is big. And here, if the slope is big, the ore is small. Now, in part C, I ask you to calculate the ore. And here it is, it's still the same. Now, what do you notice about the ore? It's getting smaller.
Smaller.
That's because the graph is going down, getting flatter. In fact, when it gets here,
It increases.
yeah. What are we talking about? The slope? What I'm trying to say is, you notice here that the ore is now constant.
It's the first one, first part. Then it's increasing.
Yeah, here the ore is big, and later the ore is small. But more important, the ore is decreasing, but then when it gets to this, what happens?
It's constant.
I said
Linear.
constant, yeah. Does anybody know why that happens for this? So what happens is with the lamp, when you turn it on, first it's cold, but then after some time it gets hot, yeah. And when it's reached its temperature, then it's sort of balanced. Do you know?
Yeah.
So like, this is like when you turn it on. But then as the voltage and current they increase, what will happen is it will get hot, and then once it's fully warm, then it stops changing. So my point is that the temperature can change the ore. I think what's happening here is when it gets hotter, the temperature changes. Yeah. But it should be getting. I wonder if I did this.
No, it's going from down 1, 2, 3, 4. That's why it's
Oh yeah, sorry, I have it backwards. What
Yeah.
idiot?
How-
Sorry. What an idiot.
Oh.
See, you said I was smart. You see, I told you it's a trick. It's a
I
trick.
believe
I'm
you're
not.
smart.
No, you shouldn't believe. Right, sorry. I screwed that up badly. I was wondering what was wrong. Yeah, here.
it's constant.
I said it backwards. Oh, I'm an idiot. Sorry. Yeah. Now, what you can't see is that it will stay flat. So what will happen is at the beginning, it's small.
Yeah.
Then as it gets hot,
Then
it gets bigger.
Yeah.
But what you can't see on the graph is later it will start to stay the same. So what you can't see, I'm sorry, is that the next one might be 0.7, 0.7, 0.7. Because once it's fully warm, you know, it might not change anymore. Yeah, I'm sorry, I screwed that up badly. So I'll just say it again. Here it's 0.5, and then later it's bigger. It's getting bigger. And it's getting bigger because this is getting smaller. Yeah, okay. Thank you for noticing that. That was terrible. Terrible. Okay, but this is okay now, is
Yeah.
it?
Yeah.
So, for things like lights, the graph usually looks like this. At the beginning, it's a line, and then it gets flatter. This is small or, and then this is big or, because this is big M, and here this is small m. What other things do you think might have this type of graph? And my hint is that if it makes a lot of heat, it's probably going to make this type of graph. So what else might you think?
Engine.
Yes. Well, something electric. Yeah, but with a computer, the voltage is very small on a computer. It's only like 5 volts. So,
Fridge.
no, you need to think about something that gets hot and you don't want it to get hot.
The processor of the computer.
Maybe the computer processor, yes. But think of something more
Maybe the
day-to-day like.
battery. The battery comes.
Yeah.
Air condition.
Yeah. Mahmood's example is a good one with the battery. So when the battery gets hot, the resistance, it will get bigger. Something else? The light, yes. I'll give you another example I can think of is, I don't know, you know when you clean the floor with the vacuum cleaner?
Yeah. Yesterday I done it.
Good job for you. If you feel it, it'll get really hot.
Yeah.
So what will happen is the ore gets bigger then. Yeah.
Or the engine for the car.
The engine, yeah, but it's, we're only talking about electrical.
Yeah, it's electric.
Electric car.
Okay. Yeah, true. For an electric car, this would happen as it gets warmer, yes. Okay, so the next part then. Is this material ohmic?
No.
No, why not?
Because it's not linear.
It's not linear. Now, before we finish, Do you think we could have this type of graph where at the beginning the resistance is big, but then later the resistance is small? So this one here is a big OR, but then later it's a small OR. Do you think this is possible?
But it's changed, like the size is changed.
Yeah. Now my question is, do you think this is possible?
Can't think of any.
Now this is possible.
Yeah.
Yeah, I know it seems odd, but this is possible. And this, I'll tell you where you find this. In the processor.
Because of the fan?
No, the processor is made from a special material that when it gets hotter, it gets less resistance. Now, if you think about that, that's kind of amazing. And this is a new material. It's only been around since like 1970.
What is it?
It's called, what do you call it? A semiconductor.
Oh.
Have you ever heard of a semiconductor? You should Google it.
Yeah.
Semiconductors are special materials like this.
Which conduct and do not conduct. I mean, they are sometimes they conduct and they do not.
Yeah, but what's special about them for the computer is that when they get hot, they have less resistance, and when they're cold, they have more resistance.
How?
Oh, that's more of a chemistry question. I think it's some property of silicon, perhaps. I'm not even sure. It's something about the material that makes it have less resistance when it gets hotter. I don't know exactly how it does it, or even what the material is, but I'm pretty sure silicon's going to be a big part of it. You know this element? Silicon? Yeah. Look it up. Look up silicon semiconductors. Yeah. All right. Is that okay for you?
Yeah.
Yeah. So look, the homework. Basically, the homework is I ask you to make 2 graphs.
That's
What? It's so easy. Just make 2 graphs.
Yeah, but I
Upside down as well.
computer.
What do you mean?
Like, what was the mistake you made? In the
No, the mistake was just in me reading.
yeah, it was the question.
Yeah. No, there wasn't anything wrong in the question. My mistake was
They was calling it.
I thought this was the start and this is the end, but this is the start and this is the
So
end.
yeah, split it. Just like the question.
No, you don't have to flip it for making the graph, because when you plot the points, it doesn't matter. You could reorder these completely and it'll be the same graph, because all you're doing is you're going 10 and 14. So if you just reorder this, all you'll do is you'll draw the points in a different order, but it won't make the graph. But it might make it easier to read if you put the smallest voltage first. This is the mistake I made. Okay. All right. We'll leave that there. Now look, you need to practice making graphs, because in the exam you will get, actually I didn't tell you this, but in every single physics exam ever, there's always one graph question. So the type of graph question could be, remember, time velocity graph, or something like this. There's always one graph question, so you do need to practice. I know it's terrible, but you need to practice.
I can draw, but I can't draw in the computer.
No.
Oh, well, that's okay. We can teach you how to draw on the computer.